finishing up lesson 32. Yesterday we talked about an antiderivative or antidifferentiation. Josiah, can you kind of explain what was happening for an antiderivative? What's the goal of that kind of question?
It's like doing the reverse.
Yeah, you're doing the reverse. You have the derivative. Our job is to write the original function. Like we saw an example where if the f of x was equal to the f prime, if the derivative is 2x. What original function, Alyssa, would give me a derivative of 2x?
X squared. No, x squared.
X squared. Okay, so x squared. Is that the only answer that she could have given me, Amelia?
Yeah.
I mean, that is a possible answer. It's actually not the only answer that we can get. So you were shaking your head no back here, Josiah. What's another answer that Alyssa could have given me?
X squared plus 17.
X squared plus 17. Because when I go to do the derivative of a constant, it just disappears. So then the derivative of the x squared still is 2x. So we noticed yesterday that when we're asked to do just an antiderivative, there's a multitude of answers that we can give, and that all just differ by a constant. Well, in today's part of our lesson about this idea of an indefinite integral, we're still following the same pattern, but we're going backwards in the question, except there's just one different thing that we're going to put at the end of our question to include all of the constants instead of just listing out whatever number I want to in our question. So today's lesson is about this idea of an indefinite integration. I'm trying to find the set of all of the antiderivatives. If I just asked you to write an antiderivative, you could give me any number of answers. Just the x squared, the x squared plus 17, x squared minus 32. All of those would be correct answers for an antiderivative, but with our integrals today, there is only one correct answer, and with this correct answer, we are including all of the antiderivatives within our answer. Now remember from yesterday, the only difference between the different answers was the constant that was at the end. Whether you had plus 17 minus 32, you could put any constant at the end and you would have the exact same antiderivative in your question. So our lesson today about the indefinite integral, so it's kind of, this is the same thing that you just wrote, you don't need to jot it down again. We are trying to get all of the antiderivatives in your question. Do not worry about writing down the next slide, it's kind of just a piece of information here. If I asked you to write so the is a singular term, one. If I asked you to write the antiderivative, that is incorrect, because you could write a whole bunch of antiderivatives. So it's incorrect to speak of the singular antiderivative, because we just saw there's two answers for the last question. X squared plus 17, x squared minus 32, x squared plus a million. There's a whole bunch of antiderivatives. But as we're looking at our lesson today, we can say give the indefinite integral. So I would just have to say give an example of an antiderivative, but I can say tell me what is the only answer that I can give if I'm going to do an indefinite integral on our question. Now, to know what's the difference between these two questions, what is the integral symbol that we're going to see in our questions? It's an elongated S that looks like this on your question. That integral symbol still tells me I'm doing an antiderivative, so I'm going backwards through the question. But as I go backwards through the question, there is only one answer that I can give in our question. Alright, so let me try to show you the difference between what we did yesterday and what we're going to see today in our questions. They're very similar, just one slight thing is going to change. Alright, so if I said the indefinite integral of 2x, 2x. Alyssa gave me one of them, and we could say x squared. Josiah gave me another example, x squared plus 17. You can say x squared plus or minus anything that you want to back here, and you would be correctly given an antiderivative of the question. Notice there is not just one answer for an antiderivative, there's an infinite number of answers on our question. Okay, so this is what we did yesterday for the antiderivative. Then I'll show you how we're going to switch that to today. It says the indefinite integral of 2x, and I'll explain all the notation here in just a second on the next slide. As long as I say x squared plus any number or minus any number, then I have correctly given an example of an of an antiderivative. Well, I want to include all of those within our answer today for the indefinite integral, so we're going to use a capital letter C to represent that constant. So here's what my answer would look like today if I asked for the indefinite integral. You would just say x squared plus c. Yesterday, if I said give me an antiderivative, we could just say x squared. We could say x squared plus 17. You actually put a number in your answer. Today, we're trying to represent all of the options that you could give by doing an indefinite integral. The only difference between all of the options was the constant that you had at the end. So all of our answers today are going to end with plus c. There are many antiderivatives, but this is the only way that I can present the indefinite integral. They're very close, it's just a minute difference. The antiderivative actually puts a number at the end. The indefinite integral puts a c at the end, representing any number that you could put back there on your question. Do you guys understand what I'm trying to explain there? So if I said give an antiderivative, you would say x squared plus 10. But if I said give the indefinite integral, you would have to say x squared plus c. You would not actually put a number there. You would represent any number that you can put back there on the question. All right, so just a couple notation things, and then we'll work through a few examples together this morning. So that constant of integration, that's the letter c that you have at the end of the question. The constant is what makes the antiderivatives different, but I'm just putting a c representing any constant as we're doing our indefinite integral this morning. The one last thing I want to show you before we get to our 4 examples this morning, the variable of integration would be the x, or it could be a y in question, and it will be indicated by a dx or a dy that you're going to see at the end of the question, so you know what variable that you are working with on the question. Okay, so again, our goal is still to go backwards. What problem would have given me this answer? Once we figure out what that problem is, we're going to end with plus c today, representing all of the answers that we could have done. Alright, so let's go ahead and attempt some questions together. Don't worry about that. I'll explain that as I do my example here. So let's start with this question. Find the indefinite integral, or find the integral of cosine x dx. Okay, so this dx just means that there's an x on the question. I'm doing an integral, I'm doing the derivative, I'm doing the differential with respect to x. Again, my job is to go backwards. What problem had a derivative of cosine? Sine. So I'm going to put sine x. That would be a perfectly acceptable answer if this was an antiderivative. But if I'm doing an indefinite integral, we're always going to end with the exact same notation. What's the last thing I need to put on my question? Plus c. Yesterday, you would number there if you wanted to. Today we're representing all of the answers possible, so any constant back there is perfectly acceptable, so I just represent that with a letter C on our question. Okay, you guys understand what I'm attempting to explain and show you there? Yes, ma'am?
So dx is not like a differential, it's just to show that x is going to be the answer?
Correct. Yeah, that just means, I mean, this is kind of a differential notation where it does say the dx, but differential and derivatives are so close to each other. I'm still going backwards looking for the antiderivative. What gave me that answer? Alright, here's our next question. So find the integral of negative sine t dt. So again, the dt tells me that I had a t in our question. So again, technically this is a differential because it ended with a dt. Again, that just clues me that it's a t, that is the variable that I'm working with on the question. What problem gave me a derivative of negative sine? Cosine. So I'm going to say cosine. Our variable is t, so I'm going to say cosine t. Again, if all I had to do was an antiderivative, I could stop. What do I need to include because I'm doing an integral? Plus c, because I can put any constant back there, and that would be perfectly fine. Alright, just have two more questions for us to finish with today. So find the integral of e to the x dx. Again, technically it's a differential because it says dx. Again, that just clues us the variable in this question is x. What problem gives me a derivative of e to the x? E to the x. What am I going to finish with today? Because I'm doing an indefinite integral? Plus c. Alright, so an antiderivative could just be e to the x. It could be e to the x plus h, e to the x minus 5. But the indefinite integral just includes all of those numbers with the letter c at the end of our question. Alright, last example for today. Now, this question, I don't see that integral symbol. What I do see is this over here. You guys remember what that notation means when it says dy over dx? That's the derivative. Okay? And notice at the end it doesn't say the dx or a dy or something. So this is more of the derivative notation as opposed to differential. But it's not changing anything about what we're doing in the question. What you have for the variable is always in the denominator. I'm doing the differential with respect to x. And there's the x that I see in the question. My job is to find the y, which is the original question. What problem gave me a derivative of cosine? Sine. And how am I going to finish my question? Plus c. Okay, so it doesn't matter if you're doing a differential, you're doing a derivative, if you're going backwards, you need to put that plus c at the end to include any number that could be at the end of your question. Yes, ma'am?
So what about that tells me that I'm going backwards? Because if that's the derivative like format, it's saying find the derivative of cosine x, isn't it? And wouldn't that be negative sine?
Okay, so what this says, it says the derivative of y, so the derivative of something with respect to x is cosine. So that's what that notation says. dy over dx is the derivative. So I'm letting the derivative equal this answer.
Okay.
What is the y? So the top notation, the dy, that means the derivative of y. The bottom notation with respect to x, that's the variable on the question. So the derivative of y is cosine. What's the y that gave me that derivative on the question? Okay, did I explain that? Are you confused? Good?
So that's saying the derivative is cosine x, and then we're trying
Yes.
to find the original.
You got it. You got it. Alrighty, so those are the only examples I have for us today. We have a couple minutes left, and I'd like you to try a couple questions out of your textbook right now. They are on, let's see here. We're going to be on page 175. And if you don't get these done, I'll have you finish them up for your homework, but I think you should be able to do them right now. Page 175, if you will do questions 5 through 8 for me. What we just talked about in our questions, some of them are kind of a very similar example of what we just saw. So questions 5 through 8 on page 175, you were doing the indefinite integral. You're always going to come up with the original